Hey everyone, this is Ed from practicalnetworking.net. Welcome to another video lesson. In this lesson, I'm going to teach you binary. The best way to understand binary is to compare it to a number system that we are familiar with, namely the decimal number system. Decimal is a number system in which we have 10 digits, which we use to represent a value. We can use any combination of these digits to represent any value we mean to represent. Now, binary is simply another number system in which there are only 2 digits to represent a quantitative value, 0 and 1. But since these are both simply number system, the rules that we are familiar with in decimal still apply to binary. The first thing I want to teach you is how to count in binary. Now, counting in binary is actually following the same rules that we are familiar with when counting in decimal. So what I want to do is highlight those rules for counting in decimal and then show you how they apply directly to counting in binary. Now, I know that you know how to count in decimal, but again, the key here is to pick out the rules that you are following that you may not even know that you are following. To count in decimal, what we do is we start by listing out the smallest value, which is 0. We then increment that value by 1 as we continue on to the next value. This is what gets us all the way to 9. Now at this point, we have run out of digits. When you run out of digits, the column that ran out of digits gets reset to 0, and the next column over gets incremented by 1. Now, every decimal digit has an implicit infinite amount of zeros to the left of it. You know this because the number 3 is the same as the number 03, which is the same as the number 003, and so on. And that's the next column over that we're going to use to increment by 1. This is how you and I get from 9 to 10. And then from here, we go right back to step 1, which has increased the rightmost column by 1. The rightmost column is currently 0. The next number in the sequence would then be a 1 in the rightmost column. And anytime you can increment a column, all the remaining columns to the left simply just carry down, which here is going to be just this 1. That is how you and I get from 10 to 11. At this point, everything continues. We have room to grow in the rightmost column, so that's going to continue incrementing along this scale. And all the left columns are simply going to be carried down. That's how we get to 12 and to 13. Now, if we continued this, we would get to 14, 15, 16, 17, 18, 19. And then here, notice we have again run out of digits in our rightmost column. So again, we will reset that column to 0, then increase the next column by 1, bringing us to 20. At this point, we can again continue to increase the rightmost column, and the columns to the left simply carry down. And the process continues. Now, let's jump ahead a bit to 94. From 94, we would get 95, 96, 97, 98, 99. And then at this point, we can't increase the rightmost column, so that gets reset to 0. We can't reset the next column over, so that gets reset to 0. So we have to increase the next column over from those implicit zeros to 1. And that's how you and I get from 99 to 100. And then from here, the process simply continues. Since we are able to increase the rightmost column, all the remaining columns simply carry down. The same thing happens if we continue forward. These are the rules that we followed for counting in decimal. What I'm going to show you is that these same rules that you already know and are familiar with decimal also apply to counting in binary. So, to count in binary, we would start by listing out the smallest value, which is 0, and then we'd continue incrementing until we run out of values, which would end after the first step, because again, there are no more values over here that we can use in the binary number system. But we can continue to use these same rules. When we run out of digits, we're going to reset the column that ran out, that's this column, and we're going to increase the next column by 1. Again, just like any other number system, there is always an infinite amount of implicit zeros to the left of every number. And so this is the column we end up incrementing to 1. Then from here, we can simply continue with step 1, increase the rightmost column by 1, so this 0 would then become a 1. And since we incremented a column, everything else would simply carry down, which would be this 1 over here, bringing us to the binary value of 1, 1. And at this point, just like we did over here, we can't increase that guy, so that guy becomes a 0. We can't increase that guy, so this guy becomes a 0. The next column over has to be increased by 1, bringing us to binary 1, 0, 0. From here, the process continues. We can increase this guy by 1. That gets us to 1. Since we were able to increment, everything else simply carries down, which brings us to binary 101. This column can't increase anymore, so we'll reset that guy to 0. This column can increase, so we'll increase that by 1. Since we were able to increment, everything else simply carries down, which brings us to binary 110. This column can increase, so that guy goes to 1, which means we carry everything else down, bringing us to binary 111. This column can't be incremented anymore, so that gets reset to 0. This column can't get incremented, so that gets reset to 0. This column can't get incremented, so that gets incremented to 0, and we increment the next column over by 1, bringing us to binary 1000. So you've seen us step through these steps to count in binary 8 times. Go ahead and pause the video right here and see if you can continue it forward another 5 times. Go ahead and pause the video. I'm going to reveal the answer in 3 seconds. Hopefully, you're able to go from 100 in binary to 1001, then 1010, then 1011, then 1100, and end on 1101. So at this point, you understand that the rules for counting in binary are the same for counting in decimal. Now, if we continued this process from here, we would end up with something that looks like this, and then something that looks like this. If we overlay on top of this the decimal counterpoints starting from 0, this gives us a correlation between the binary numbers and the decimal numbers. We know that binary 10 correlates to decimal 2, and binary 10100 correlates to decimal 20, and binary 100101 correlates to decimal 37. Now that's one way of converting binary numbers to decimal numbers, but there's actually another way that doesn't involve simply counting out every decimal number until you get to the binary number you're trying to convert. That's what I'd like to show you next. This is a decimal number. Now we know this because it uses numbers other than simply 1 and 0. You and I know this number as 506,207. You and I can interpret the value of this number because we've been taught that this number equates to a 5 in the 100,000ths place value, 0 in the 10,000ths place value, 6 in the 1,000ths place value, 2 in the 100ths place value, 0 in the 10s place value, and 7 in the 1s place value. Breaking out a number like this can also be done in binary. This is a binary number. This binary number is a 1 in the 100,000 place value, a 0 in the 100,000 place value, a 1 in the 100,000 place value, a 0 in the 100 place value, a 1 in the 10, or a 1 in the 1 value. So for us to convert this number into decimal, all we really need to know is what each of these equate out to in decimal. Then we can simply add them together or not, depending on whether we have a 1 or a 0 in this column. If we go back to our binary counting exercise, we can map out every place in binary where we had to add an additional column. Here we had 1 binary column, here we had 2, here we had 3, 4, 5, and 6. The correlating values in decimal are the numbers we need to do the binary conversion. So if we take those values, 1, 2, 4, 8, 16, and 32, and apply them to what we had before, we can easily deduce what this binary number is. Since there is a 1 here, we are going to add 32. Since there is a 0 here, we're not going to add 16. Since there's a 1 here, we are going to add 8. 0 here, we're not going to add 4. A 1 here, so we are going to add 2. And a 1 here, so we are going to add 1. If we add 32 plus 8 plus 0 plus 2 plus 1, we end up with a value of 43, which means this binary number equates to 43. We have just done our first binary conversion. Now I want to highlight something for you. Notice these values over here. They have a pattern. To get from this value to this value, we simply multiplied by 2. To get from 2 to 4, we again multiplied by 2. For each value in the sequence, we simply multiplied by 2 to get the next value in the sequence. What do you think the place value would be for this binary digit? If you guessed 64, then you guessed correctly. We could keep going one more to get 128. We could continue from here to get 256, but for now, we'll stop here. These values can be used to translate any binary number into its decimal counterpart. So let's list out those values in a table, and let's throw a binary number into our table and see if we can calculate what that number is in decimal. The key is, just like we did before, wherever there's a 1, we're going to add that column's value. So since there's a 1 here, we're going to add 32. Since there's a 1 here, we're going to add 8. Since there's a 1 here, we're going to add 2. And since there's a 1 here, we're going to add 1. If you add 32 plus 8 plus 2 plus 1, you end up with 43. Now, if that looks familiar to you, it's because it's the exact same thing we just did a minute ago, except we use this shortcut table to do it. Now let's go ahead and do another one. Here's another binary number. This number has a 1 here, so we are going to add 16. Has a 1 here, so we are going to add 1. If we add those two together, 16 plus 1 means that this binary value equals 17. Let's do one more. Here we have another binary digit. To convert this to decimal, we're going to add 128 plus 16 plus 4 plus 2. If we add those together, we end up with 150. Now it's your turn. Go ahead and pause the video and see if you can do this binary conversion. I'm going to give you the answer in 3 seconds. Hopefully, you're able to deduce that that binary value equated out to 170. You would have got that by adding 128 plus 32 plus 8 plus 2. Now I have another 3 that I want you to try. These 3. Now you might be thinking to yourself, oh, I think I already know, I don't need to practice. But something interesting is going to happen with these 3, and I want you to see it for yourself. So go ahead and pause the video and do the binary conversions for these 3 values. I'll reveal the answer in 5 seconds. If you added all the values for this binary digit, you would have been adding 32 plus 16 plus 8 plus 4 plus 2 plus 1. That should have gotten you a result of 63. This one is pretty straightforward. There was only a single 1 in the 64's placement, so all you had to do was add 64, which gets you 64. And this third one was also fairly simple. You're adding 64 plus 1 to get you 65. Now notice these values are sequential. Do you remember our rules for binary counting? If all of these columns are 1, they would all get reset to 0, and the next column over would increment to 1. From here, since we're able to increment this column by 1, all the remaining columns simply carry down. So everything we just learned insofar as binary counting still applies, and you're seeing it as we're doing the binary conversions. So hopefully that helps you tie together what we learned prior. Now let's do a couple more. This binary value should be pretty straightforward. If we have all zeros, the correlating decimal value will also be 0. What if we had all 1s? Well, that would mean we would have to add every value in this table. So if we pull up a calculator and add 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, we would get 255. So we just learned how to convert binary digits into decimal. But you can use this table in the opposite direction as well. You can convert a decimal number back into binary. To do that, we have to find the right combination of 1s and 0s in these columns such that some of these values will add up to the value we are targeting for. Now, with these conversions, keep in mind, only one combination of ones and zeros will add up to 229. So we just have to find that one combination. The best way to do this would be to start from the biggest place value, 128. What we do is ask ourselves, can we subtract 128 from 229? We sure can. So we'll set that column to 1, and then we'll subtract 128 from 229. And that'll get you 101. Now we need to account for this value. Can we subtract 64 from 101? We sure can. So we'll set that column to 1. And then we'll subtract 64 from 101. And that'll get us 37. And then we continue. Can we subtract 32 from 37? We sure can. So that's a 1. If we subtract out 32, we are left over with 5. Can we subtract 16 from 5? No, we cannot. So that column is a 0. Can we subtract 8 from 5? No, we cannot. That column is a 0. Can we subtract 4 from 5? Yes, we can. So this column is a 1. And then we subtract out 4, leaving us with 1. Can we subtract 2 from 1? No, we cannot. That column is a 0. Can we subtract 1 from 1? Yes, we can. And we end up with 0, which means the decimal digit 229 correlates to the binary value of 111,00101. Now let's do one more. This is the decimal value of 76. We'll again go through the same process, starting from the biggest. Can you subtract 128 from 76? No, you cannot, so that column is 0. Can you subtract 64 from 76? Yes, you can, so that column is a 1. We'll subtract out 64. 76 minus 64 is 12. Can you subtract 32 from 12? No, you cannot, that's a 0. Can you subtract 16 from 12? No, you cannot, that is a 0. Can you subtract 8 from 12? Yes, you can. You're left with 4, which means that column is a 1. Can you subtract 4 from 4? Yes, you can. That column is a 1. We subtract 4, giving us to 0. You can't subtract 2 from 0, so that's a 0. You can't subtract 1 from 0, so that's a 0, meaning the decimal value of 76 equates out to the binary number of 01001100. Now that you've seen the process in action twice, go ahead and see if you can figure it out for this one. Go ahead and convert this decimal value into its binary counterpart. Pause the video, and I'll give you the answer in 3 seconds. Hopefully, you're able to deduce that the decimal value 163 equates out to the binary value of 10100011. Now I have another 3 that I want you to do. And once again, something interesting will be happening with these 3. You'll be able to tie back in this conversion to what we learned earlier about binary counting. So go ahead and convert these 3 decimal numbers into their binary counterparts. Go ahead and pause the video. I'll give you the answer in 5 seconds. So 127 in decimal calculates out to 0,111,1111 in binary. 128 in decimal, that one should have been pretty easy. Can you subtract 128 from 128? Yes, you can. That gets you 0, which means everything else is simply going to be 0. 129 also should have been fairly straightforward. The result would have been 10000001. Now again, you'll notice that these 3 are sequential. If we were counting in binary, since all of these columns are 1, they would all get reset to 0, and the next column over would get incremented by 1. From here to here, since this column was able to get incremented by 1, all the remaining columns simply carry down to get you this binary number right here. Now let's do 2 more. This one will be pretty straightforward. The decimal value of 0 correlates to the binary value of all zeros. Here's another decimal number. Now, we did this in the last section, so you might remember what this correlates to in binary. But I want you to see it, because I think that's important. So let's bust out our calculator. We'll do 255 minus 128. That gets us 127. 127 minus 64. That gets us 63. 63 minus 32, that gets us 31. 31 minus 16, that gets us 15. 15 minus 8 gets us 7. 7 minus 4 gets us 3. 3 minus 2 gets us 1. And 1 minus 1 gets us 0. So we confirmed that 255 equals all ones in binary and all ones equals 255 in decimal. Now you might be wondering, why did I have you do those two twice? Well, those two are sort of important. They're important because they give you the lower and upper bounds of any 8-digit binary number. Now, a digit in binary in the computing world is called a bit, which means 0 and 255 are the smallest and largest 8-bit number. Now, why that's important is because IPv4 addresses are 32 bits long, and the way they are represented is we break up those 32 bits into 4 equal chunks. We call each of those chunks an octet, and each of those octets represent 8 bits, which means the smallest value you'll ever see in each of those octets is 0, and the largest you'll ever see is 255. This is why you'll never see an IP address with the value 256 in it, or 300 or something like that, because we simply don't have enough bits to account for numbers this big. So, to summarize, we started out by learning that binary is simply a number system composed of either 0 or 1. We then learned how to count in binary. Then we learned how to convert binary numbers into decimal numbers, and then we learned how to convert decimal numbers back into binary numbers. And that, my friends, wraps up our lesson on binary. I hope now you find yourself in this group of people. If you enjoyed this lesson, please share this video with a friend, classmate, or colleague, and don't forget to like and subscribe. Otherwise, I want to thank you for watching, and I'll see you in the next video.